Hi guys, this is part 2. This is, file number 2, video number 2 of the STAV 2021 Unit 3 and 4 trial examination. This is the beginning of section B. Questions 1 to 9 are going to be on this file, on this video. So if you're looking for an explanation for questions 10 to 18, you've got the wrong video. All right, let's get into it. Question 1. As per usual, I'm assuming that you have the document with you. Pair of charged parallel plates have a potential difference of 100 volts between them. They're 5 millimeters apart. What is the magnitude of the electric field between the plates? Fairly easy. They're checking if you know this formula, V equals ED, on the formula sheet, I believe. Rearrange it. The only thing you need to remember is to get the units right. Change millimeters to meters. Pretty straightforward. 2 by 10 to the 4 volts per meter. That's the answer. Excuse me. Part B. An electron is stationary very close to the surface of the right-hand plate when the plate voltage is applied. Right? The right-hand plate is the negative one, so it's going to move quite away from that plate to the left. What is the speed of the electron when it impacts the left-hand plate? Now, this is a change of energy thing, right? This is the formula for the electric energy, right? E equals QV. So when the power is connected, that amount of electricity that amount of potential energy is given to the electron, right? The charge on the electron times the voltage between it, which was 100 volts. And that is going to change into kinetic energy, right? By the time the electron gets to the other plate, it'll have none of that left. It'll have no electric potential energy left at all, because when it's on that positive plate, if you let go of it, it doesn't go anywhere. However, it's going to slam into that plate with a significant velocity, right? So that energy turns into that energy, and you just have to solve this for the velocity. Excuse me. Now, and the answer came to 5.9 by 10 to the 6 meters per second, as the solutions tells you. All right, part C. One of those things that a lot of people are going to get wrong here. Question C, let me have a look at this. I've just got to get the reading of the question. All right. If the distance between the plates is reduced, will the impact speed of the electron with the left-hand plate increase, decrease, or be unchanged? It's not going to change. And here's why. Let me just show you something here. If there are two plates that far apart and they have a potential difference of 100 volts between them, because they are far apart, excuse me, the sort of density, the rate of change of voltage from one side to the other is reasonably low. So if that's negative and that's positive, and we've got an electron there, it's going to head that way. But as it goes from there to there, it's going to lose, say, 10 out of that 100 volts of potential energy. Right? If you bring the plates closer together, and that's still 100 volts, right? And we put that electron there, and that's negative and that's positive, right? When the electron goes that far again, right, from there to there, let's put those two dots there, that's now going to lose maybe 80 volts, right? Maybe 80 joules of potential energy, because it's done most of the 100 volts in a short amount of time. So in other words, the closer the plates are together, the more power this thing has, right? The more rapidly the energy changes from one to the other. And the greater the acceleration of the electron is. In both cases, the final speed ends up being the same. Right? So it's going to slam into that at 5.9 by 10 to the 6, and if you bring them closer together, it's going to slam into that at 5.9 by 10 to the 6. It's just going to have to accelerate faster to do it, but it will end up having exactly the same kinetic energy as, you know, there or there. It doesn't matter how far the plates are apart. And the other way to explain that away is that basically the distance between the plates is not in the above equation. So if it was a contributing factor to the velocity, it would have to turn up in the equation. Anything that's not here is not going to affect the velocity. So clearly the mass of something will affect it, right? The voltage between the plates, if that had been 200 volts instead of 100 volts, that would have affected it. And if the electron had been 10 electrons instead of 1 electron with 10 times as much charge, that would have affected, but nothing else will. Question 2, have a look at it, get it in front of you. A proton with that mass, with a velocity of that, passes into a magnetic field. They've given you the picture there, and it bends itself into a circular path. So here is the question in question. There's the diagram, just in case you don't have it in front of you. Excuse me. It passes into the magnetic field. This is the boundary of the magnetic field, and the magnetic field strength is 0.25 Teslas, and it's oriented perpendicular to the initial velocity of the proton, right? So in other words, the magnetic field is not orientated that way or that way, right? Perpendicular could mean up, that makes a right angle, or down, or into the page or out of the page. So there's still 4 choices, or anywhere like this, right? It could be diagonally going up, and that's still making a right angle with that horizontal line, right? So there's actually an infinite number of ways that magnetic field can still be perpendicular to that. Right? So they didn't really give away the direction of it. The path of the proton is shown in the diagram, right? The area of the magnetic field is shown, but the actual magnetic field lines aren't there, right? What is the radius of the path? Okay, so this first one is just a simple calculation. If this isn't on your cheat sheet, whack it on your cheat sheet. It's quite handy. You can get it. It comes from this, right? It comes from the reason that this happens, okay? mv squared on r is the force required to put anything into a circular path, right? Whether it's a car, an aircraft, an electron, anything at all, okay? So in order to get that proton doing that circle, you need this much force, right? In this particular case, that is the source of that force, right? This is the force on a charged object in a magnetic field, F equals QVB, right? We've seen that 100 times. So that is the cause of this. So they must be equal in this particular case. And you can solve that and juggle it around. You'll get this formula here for R, and that'll get you what the radius of this curve is, right? Just put all the right things in. And again, they've been nice to you. They've given it in the masses in kilograms. That's in Teslas. That's in meters per second. So you don't have to change any units. Just throw them all in the right form there and away you go. All right, secondly, part B, they asked you to draw on the diagram, excuse me, to draw on the diagram the direction of the magnetic field, okay? So you're going to draw dots on it. And the reason for this is you're going to do the right-hand rule, right? The whole stop sign right-hand rule, not this one, right? So positive, right hand, positive. Thumb going there, right? It ended up being forced in this direction, right? Now, something that's going in a circle is being forced towards the center of the circle. The center of that circle is about there. So at that position there, we have an object going that way, being forced that way. So I have to get my palm pushing that way, my right palm pushing that way, and my right thumb pushing that way. And the only way to do that is to do this. And my fingers are coming up straight up to you. So my fingers represent the magnetic field. So you just had to draw a bunch of evenly spaced dots. Do them evenly spaced. Because if you do this, if you have a little pocket here where there's more of them together, that tells the person marking the exam that you think that the magnetic field is stronger there and weaker there, which is wrong. So make sure they're reasonably evenly spaced. Don't sit there with a ruler and get a millimeter perfect, right? But space them out roughly evenly. That'll be fine. All right. Okay, question 3. This is another one that I'll put the diagram up here for you. Let's have a look at this. A closed square loop of wire, this is the loop of wire, is passed from outside a magnetic field through it and ends up completely out of it again. This is where the magnetic field is. Right? The situation is shown. Right? The current flows in an anti-clockwise direction around the closed square loop of wire as it passes into the magnetic field. All right, I'm going to redraw this on a blank piece of paper, mainly so I don't screw up the other side of this page, just in case we need it. Just hold on a second. All right. So there is the area of the magnetic field. Here is the loop passing into it. We're moving it that way. Now the question says, we'll get back to that in a second. The question says, what is the direction of the magnetic field inside the dash box? So we have to like draw lines up or down or out of the page or whatever. All right, let's have a look at this. We know that as this is going into the magnetic field, a current is induced anti-clockwise. Anti-clockwise is that way. Current flows anti-clockwise. Okay, so imagine you are a charge. You are a positive charge right there, sitting in that wire. Right? So I'm going to use right hand because I picked a positive charge. I didn't say electron. And they said regular current, so we're doing right hand rule. Okay, that, as long as I'm dragging the whole wire this way, that charge is going this way, right? So again, right hand rule like this, the thumb has to be going that way because that's where every single charge in that loop of wire is being dragged. They're all going that way, and this one is going that way inside a magnetic field, so it's going to be moved. And it's clearly being moved that way, up the page. All right. So I have to get my thumb going that way and my palm going up. So the only way to do that is for me to stand up and do this. Right? And my fingers are pointing down into the page. So only a magnetic field that looks like this, pointing into the page, is going to have that result from that motion. Okay. Which is why the answer is into the page. And it's enough of an explanation just to do this. Right hand rule, thumb points right, palm points up, therefore fingers are into the page. That's fine. That's perfect explanation. That's 2 out of 2. And I chose to give you this explanation because the STAV solutions document gives you a different explanation. You can use Lenz's law for this one as well. I just thought I'd give you 2 different explanations now. Okay, question 4, something completely different. It has a tractor of mass 4,500 kilograms pulling an empty trailer of mass 1,800 kilograms along a horizontal road, right, going that way. The tractor and trailer accelerate forward from rest at a constant rate of 0.1 meters per second squared. That's the acceleration. Calculate the speed of the tractor after they've been doing that for 10 meters. Okay, this is a pretty straightforward question. Again, when in doubt, write this list down, right? Every time. If you don't quite know which formula to use, do that and you'll figure it out. It'll literally tell you. You've got to find something with a U, A, S, and V. Started off at 0 because it was accelerating from rest. They gave you the acceleration, 10 meters. How fast is it going now? Right. V squared equals U squared plus 2AS. Solve it. Everything's in the right units, 1.4 meters per second. Easy. Now, what most people don't find so easy is the next question. Excuse me. Part B says the trailer experiences a total frictional resistance of 1,200 newtons. Calculate the tension in the coupling between the tractor and the trailer. Okay. When you're trying to figure out tension questions, you only consider one of the objects, right? You go for one end of the string or one end of the tow bar or whatever, or the other. You're either considering just the tractor or just the trailer. I've considered just the trailer because the friction is on the trailer. I can use that. I can't use that if I'm considering the tractor. All right. So the net force on this trailer will equal MA. Right? There can be lots of forces, but there's only one acceleration. So the acceleration is caused by the sum of all of the forces on something. We've done that 100 times. All right. So all the forces added up equals MA. And that is the tension trying to pull it forward, and the friction is trying to pull it backwards. So they are against each other. So I have to go one minus the other. Right? So the tension minus 1,200 equals MA. That's the M of the trailer, and that's the acceleration of the trailer. It's the acceleration of everything. And again, all of this is for the trailer. Force on the trailer, mass of the trailer, etc. Keep it for the same thing. Don't mix stuff up. Solve that. Tension is 1,380 newtons. Now this next one is an interesting question. This is a momentum question in disguise. Normally a momentum question is very obvious because it says there's a collision of some description. Right? And nearly every collisions question is about conserving momentum. But this is a momentum question in disguise. They've really hidden it well. A lot of people will not know where to start on question C. Here it is. Let's have a look at it. The tractor and the trailer roll unpowered. Right? So they're not underpowered. They're just rolling at a constant velocity at 3 meters per second. Right? They're just cruising underneath a hopper at a speed of 3 as the trailer passes over the hopper, 1,200 kilograms of fertilizer is dumped onto it. So basically, a stationary object weighing 1,200 kilograms has hit this moving object weighing moving at 3 meters per second. Right? That is actually a collision. All right. So what is the speed of the tractor and trailer immediately after that load got dumped into it? Right. Remember, the engine isn't pulling it yet. Right. The farmer has got his foot on the clutch, or it's just coasting in neutral. Right. So that is going to slow this thing down. Let's figure out how. So it is a collision. Momentum before equals momentum after. Right. The total momentum of the tractor and the trailer before. And that before, keep in mind that this had a momentum of nothing before because it wasn't moving, equals the total momentum of everything after. So this collection here, 4,500 and 1,800, that's 6,300 kilograms. So the total momentum of everything that was moving is 6,300 times 3, mass times velocity. That's beforehand. After, this didn't weigh 6,300, it weighed 7,500 because it had this extra 1,200 on it. So it's weighing that much, and it's going at a new velocity that we have to find out. So that is how you set this question up, and you solve that formula and you get this answer. A lot of people are not even going to realize that that's a momentum question because they don't realize that that is actually a collision, but it is. Now part D, just in case you thought you were out of this question, it says, is this collision elastic or inelastic? It is inelastic, and the way you find this out, it is an elastic collision if kinetic energy is conserved. So you do exactly this thing, but you don't do it with mv, you do it with a half mv squared. So you do this again with a half mv squared over there and a half mv squared over here, and you find, and your new v, and you find out whether that equals that. And in this particular case, it doesn't. So it's an inelastic collision. Question 5, projectile motion. Everyone's worst nightmare. I don't know why. I think it's pretty easy, but I respect the fact that it's everyone's worst nightmare. Okay, a cricket player, here it is. A cricket player hits a cricket ball from the middle of the ground over the fence into an advertising screen. Into there. The ball leaves the bat with a velocity of 40 meters per second at an angle of 20 degrees to the horizontal. Okay. The ball is hit from a height of 0.5 meters above the ground. That's about knee height. And the advertising screen is a distance of 85 meters horizontally from where the ball was struck. All right. They illustrated the situation from side on. Excuse me. Let's put that down a little bit. And question A says, from leaving the bat, how long is the ball in the air before hitting the advertising screen? All right, rule number 1, pardon me, rule number 1 of projectile motion, do this. Right? You don't do this, you are in trouble. Right? The vertical formulas and the horizontal formulas have to be kept different to each other. In the previous exam that I did this for, I gave you the list of vertical and horizontal formulae to put in your cheat sheet. You should have them there now. But you have to look at every single projectile motion question like this. You say, what's vertical and what's horizontal? The vertical things that you know is that the initial velocity is the vertical component of that, right? And the vertical component of that going that way is 40 times the sine of 20. Right? And the horizontal component, by the way, is 40 times the cos of 20. So vertically, we know the initial velocity is 40 sine 20, and it accelerates downwards at negative 9.8. Negative because it's going down, positive because that's going up. All right. Horizontally, there is only one velocity horizontally. There is no acceleration horizontally, so u is the same all the way along. It won't change into a different v. And it's 40 cos 20, as I just said, and the distance that it goes is 85 meters, right? That's all we know, right? There is one horizontal formula, and this is it, right? Velocity equals displacement over time. We've got two of these things. We can find the time. This is what they're asking us for. T equals S on V, 85 divided by 40 cos 20, and it comes to 2.26 seconds. So that's how to do question 1. But if you get this wrong, you're going to get everything wrong, right? This is where all the brain power is. This is grade 8 maths, right? Part B. So, don't pat yourself on the back too much for getting that right. Get this right and you're a genius. All right. Part B, excuse me. It said at what height above the ground does the ball hit the advertising screen? So they're after that distance there. This is a vertical question because that's a vertical thing. So you have to use vertical figures. So we're not doing that anymore. All right, vertical stuff. You know A. You know the time now. You know that it was flying for 2.26 seconds. The time is the only thing that isn't on one side or another. It's on both. All right. So you've got U, A, T, and you have to find S. You have to find the vertical distance, right? The vertical displacement of it. So again, once you've got this list right, you just pick the formula from your arsenal of formulas that works for it. And S equals UT plus half AT squared will do the job. It's a little bit of painful maths, a lot of button pushing, but you end up getting 5.88 meters. Now, this is what you need to know. A lot of people are going to stop there and think they've got the right answer. They haven't got the right answer because that is a displacement. That is from half a meter above the ground. So that from there to there, that is the 5.88 meters. Now the question said how far above the ground did it hit? It hit the side screen, it hit the advertising board 5.88 meters above that spot, which is like another 0.5 meters above the ground. So you had to add the 0.5 onto it to get 6.38. That's how you do it. I cannot emphasize too heavily, you've got to do this. If you don't do that and set it out like this, you're going to lose this terribly, right? You're going to put one wrong figure in here somewhere and not even know it, and you're going to get a crazy answer. All right, that's how to do it. Question 6 about the International Space Station orbiting the Earth at an average altitude of 420 kilometers above the Earth's surface. What's the orbital period of the ISS? Give your answer in seconds, or the answer comes out in seconds, which is quite handy. This is a Kepler's third law question. The only way to do this is know this formula, okay? They gave you the orbital period, did they? Sorry, they gave you the radius, and they're asking for the orbital period. All of that is a constant, right? Pi's constant, G's constant, M's constant. The M is the Earth's mass. Again, the capital M in the gravity formulas is the mass of the thing in the middle. It's not the mass of the thing going around. All right. So you need to read the Earth's mass. You're going to be given that in the formula sheet. You're going to be given G in the formula sheet. So all of this is easily known. Right. The Earth's radius is on the formula sheet as well. So you have to go the Earth's radius plus 420 kilometers. So that's the radius of the circle around which the ISS travels. Get all that right and you will end up getting the right answer in seconds, right? So this has to be in meters, by the way, right? Just like everything else, the mass of the Earth has to be in kilograms. The period is going to come out in seconds. The radius has to be in meters. So you're dealing with some very big and very small numbers here, right? But you're just going to have to get used to that. All right. For part B, it says what is the Earth's gravitational field at the position of the ISS? Again, we've seen this one before in the multi-choice questions. This is how to figure it out. GM again, you can just copy it from this, divided by r squared, the same r, and you're going to get 8.65 meters per second squared, a little bit less than it is at the surface, which is what you'd expect. Part C is a bit of an explanation question. An astronaut working on the ISS is floating in space relative to her workstation. 2 students on Earth are observing her work through a live TV connection. One student, Sarah, states that the astronaut is experiencing zero gravity as she floats in the space station, while the other student, Mary, disputes it. Is Sarah correct? No, Sarah is not. So the first thing to do is actually answer the question, and they've made it easy for you because they did this. They said circle your choice, so do it. Circle your choice. If they say circle your choice and you tick it, you can't get it right. Right? That is a wrong answer. Circle your choice. That's now a right answer. Right? Do exactly what the question says. Right. All right. So now it says explain your choice. The next thing, explain your choice. Why did you do that? Well, here's the reason. You just calculated the value of gravity in part B. Gravity is not zero. at the International Space Station because people are floating. Gravity is 8.65 meters per second, right? Check answer B, right? That's all you have to say. Easy. Question 7, I've got the diagram on here. Alternator in the diagram below has a rectangular coil, sides of 0.2 meters by 0.15 meters, and 40 turns. The coil rotates at a rate of 20 revolutions per second in a uniform magnetic field. The magnetic flux through the coil is that. Okay. Slip rings, fair enough, no worries. The question goes like this. On this particular exam, they have the formula sheet right in the middle, so you have to go about 4 pages further down, and then you finally get this question. A graph of the output voltage of the alternator through the slip rings is shown below. Okay, again, it's a graph. Stop and look at it. All right. EMF, they didn't give you any numbers here. They just said voltage peak and not negative voltage peak. Period, 2 periods, time in seconds. Okay, right. Based on the information in the previous diagram, what is the value of t on the graph above? Now, t is the time that that thing takes to go around once, because this is a complete wave and that is caused by a complete revolution. All right, so we're trying to figure out how long it takes to go around once. And the question said it rotates at a rate of 20 revolutions per second. So it should take 1/20th of a second to go around once. Or you could just use the formula, like I did. Period is 1 on frequency, 0.05 seconds. Either way, either explain it the way I did, or just use the formula. Okay, part B says what's the magnitude of the average voltage output of this thing as it's rotating? Okay, the average voltage is always the number of turns times the rate of change of flux. Okay, 40 turns. Now, it goes from maximum flux to minimum flux in a quarter of a turn. Keep this in mind. Right? That's maximum flux. That's the greatest number of lines of magnetic field going through that rectangular loop. Once it's done a quarter of a turn and it's like that, horizontal, right, it's going to have no flux going through the loop because the whole loop's going to be horizontal and all of those lines are going to be missing it rather than going through it. And that takes a quarter of a turn. So it takes 1/4 of 1/20th of a second to do that. So that's where I got this from. Right? The change in flux, it goes from a flux of 0.25, which was the maximum they gave it to us, down to 0 in, that is a quarter of 1/20th of a second. Okay, figure that out, 800 volts. Part C, it says if the slip rings of the alternator are replaced by a split ring commutator, draw the graph of the alternator output. Now, if all the other settings are kept the same. All the other settings are kept the same, which means it goes round at the same speed. And if it goes round at the same speed, it's going to take just as long to do one of these hops. Right? So that's going to be the same, and it's going to go just as high as well. If it was rotating faster, you'd have to accordion that a little bit. You have to make it skinnier and taller, because the faster it goes, the more voltage it gives. Right? But luckily, they've been nice to us, and they've said, look, nothing else is changing. Okay. Now, split ring commutators, they change alternating current, which is this, positive, negative, to this, positive, 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 positive. So this is what you're doing. All you're doing is reversing these two negatives and making them positive as well. No one is going to care how good or bad your parabolas look, right? That dodgy thing that I've just done in an orange texture is full marks. Right? What matters is that you've got the peak at the same height as it should be, and you've got the frequency the same as it was before. Right? One rotation still takes half of the whole graph, and the next rotation takes the rest of the whole graph. They're the only two things that matter, and that's where you get your 2 marks from. Here's question 8. A diagram of a simple DC motor this time. So this is taking in electricity and we're causing it to move. We're not using movement to make electricity. So there's no There's no EMF being produced here. It's the other way around. It's a simple DC motor as shown. The side length is 3.5 centimeters, so AD, so that's 3.5 centimeters. And the width of the coil is 2 centimeters, right there. Okay. The coil is formed by 50 loops of copper wire. The field between the magnetic field poles is 0.15 Teslas. Power supply is 4 volts. Let's see. Current is, 4 volts and a half an amp of current. Okay. At the position of the coil shown in the diagram above, what is the magnitude of force on the side AD? Now this is the point where the force is maximum, because the rate of change of flux is biggest when the flux is actually 0. When there is none of those horizontal lines of magnetic field going through the loop, the rate at which that changes is maximum, because part of the loop is going vertical, in fact vertically up, and the other half is going vertically down. I don't know whether I got which one right. And this is the moment at which the change of flux is the greatest. Excuse me. So this is going to be the maximum. And there's a formula for that. F equals NBIL. They gave you all of those things. Put them all together, multiply them all out, and you get that. Okay, pretty easy. Just watch the units. Again, the only units we're going to have to change here is centimeters when we get to use those, but everything else was fine. So that's pretty straightforward. Right, part B, it says on the diagram above, indicate which arrow the direction of the force on side AD is. Okay, side AD. Right, you have to follow, you can use left hand or right hand, but just make sure you've got the right thing. I'm going to use left hand because every time I see this thing, I just tend to sort of imagine that arrow that I've shown you guys a lot, showing me where the electrons are going. So electrons is left, so the electrons are going in from D to A, and they're going to come out from B to C, right? That's how they're going. So left hand, electrons going in. My fingers have to go from north to south, so I've got to have my fingers going that way and my thumb going into the page, and I've got to figure out where my palm goes. So it's going to end up being a little bit like that, right? And my palm is facing down. So side AD goes down, so you have to go like that and make it really obvious, right? Big, fat, obvious, red, colorful arrow, right? Don't make it missable. Right? That's the answer. It says on the diagram, indicate with an arrow the direction of the force. Make it obvious, make it plain, make it huge. You don't want people to miss it. All right. Part C, the motor is spinning at a steady rate and give 2 changes to the setup that you could make to increase the speed of rotation. Now I've just said here C document because they listed about 6 of them, or in fact 5 of them in the solutions document. All right. Now they've given you quite a wide range here because they didn't say changes to the apparatus. They just said, what can you change about this setup, right? You've got a motor here, you can make it more powerful, right? More voltage, more current, that would help. You could make the magnet stronger, increase the magnetic field strength. You could bring the North Pole and the South Pole closer, if you could. You could make the coil bigger, right? Increase the area. Excuse me. You can increase the number of turns. You could use loops made of wire that has a lower resistance. You can lower the friction between the split ring commutator and the brushes. There's quite a few things you could do. Any 2, and like I've said all the time, do exactly what the question says. It gives you 2 things. Don't list more than 2. Just do 2. Okay, question 9 does a lot of people's heads in. This is a tough one. Let me get this a little bit more central. Okay, there's a magnet. I'm going to use my little magnet in a minute. This is the setup. It's a solenoid. It's a loop of wire, lots of loops of wire curling around a tube, an empty tube, and there's a resistor there, and we have to move a magnet somehow to make conventional current go that way through the resistor. Okay, let's investigate this. I think the simplest way for me to do this is if I need the current to go that way here, I need it to go that way here. And I need it to come out of the page there, right? So the current is going to go out of the page, down the page, and across there. Right? So I need to make positive charges come out of the page there. Okay, so I've got it. So I'm going to try something here. South pole. Magnetic field lines go in towards a south pole. They go away from north and towards south. So if I put that south pole right there, if I put it right there in fact, then at the moment there are magnetic field lines going in there surrounding this particular positive charge that isn't moving yet. Right? If nothing's changing, it isn't moving. But if I move this magnet that way, then suddenly these two magnetic field lines are going to move that way. And that's the equivalent of the charge moving that way in a magnetic field. Right? Now it's conventional current, so I have to use my right hand. Right? A charge moving that way in a magnetic field going that way would be forced into the page. The only way I can get my thumb going that way and my fingers going down there is to put my right palm straight down. I've got to sort of get up off the chair and do this. And in order for this to happen, it has to come out of the page, not into the page. So clearly, if I was to move this magnet out, that would be the wrong answer. In other words, moving it in is going to be the right answer. So one of the answers is push a south pole into the left-hand side of the coil. Now the absolute opposite will work as well, right? Once you've got one answer, the other answer is reasonably obvious. Pushing a south pole into that side will have the same effect as pulling a north pole out. Right? That will do the same thing. Right? It's a different direction, but it's also arrows going the different way. So those two 180-degree differences cancel each other out and you get the same answer. Okay? So once you've got one of these things, the other one pretty much writes itself. So you can say pull a north pole out of the left-hand side. Again, it asks you for two ways. Once you get one way, just literally say the very opposite way, right? Push, pull, south, north, into, out of, right? The only thing that's the same is which end you're doing it to. All right, interesting question. That can confuse a lot of people. All right, that's the end of this video. I'm going to do questions 10 to 18 in the next one. See you there.